In this video, we will look at compound inequalities which use the operator AND. A compound inequality has many inequalities. When we're using the operator AND to connect those inequalities, we mean that they are all true. And that is what we will attempt to solve for. When solving inequalities, we remember it's just like solving equations. We just need to be sure about one thing, and that is to flip the symbol when we either multiply or divide by a negative. Let's take a look at some examples where we can see these inequalities worked out. In this problem, we see AND is connecting two inequalities. We can solve them individually. The first by subtracting 5 from both sides. Gives us 6x is less than 6. And finally, dividing by 6 gives us x is less than 1. And for the other inequality, we simply subtract 2, and we get negative 7x is less than or equal to 42. And finally, divide by negative 7. Notice we've divided by a negative, which means we need to flip the inequality symbol the other direction. X is greater than or equal to negative 6. You may remember from inequalities in the past that we can graph these inequalities on a number line. Starting with the first inequality, we're going to float it above the number line. Starting at 1, we can use an open circle, showing that we're not equal to, strictly less than, and less than means the graph goes down. The other graph, starting at negative 6, with a closed circle, showing that it's equal to that value, and the x is greater than, going up. When we use the operator AND, we want both to be true, meaning we want these graphs to overlap. We notice they overlap in the middle, at negative 6 with the closed dot, and 1 with an open dot, and everything in the middle. This means any value between these will make both inequalities true. We can express this in interval notation as well, negative 6 being the low number, with a square bracket representing or equal to, and 1 the top number with a curved bracket. Let's take a look at a problem that's a little more involved, where we do this exact process again, looking for the overlap when both inequalities are true. In this problem, we must start by getting the variables on the same side, by subtracting 3x from both. We get 8x minus 10 is greater than negative 2. Next, we can add 10 to both sides to get 8x is greater than 8. Finally, dividing both sides by 8, we end up with x is greater than 1. And to solve the other inequality, we can start by distributing through the parentheses. 18x plus 6 minus 2 is greater than or equal to 10x plus 52. After distributing, we often combine like terms, giving us 18x plus 4 is greater than or equal to 10x plus 52. Moving the variables to one side, we subtract 10x. 8x plus 4 is greater than or equal to 52. And finally, we subtract 4. 8x is greater than or equal to 48, and divide by 8. X is greater than or equal to 6. Again, we can put these on a number line, starting with the first inequality at 1, open circle, because it's just greater than, going bigger. And the second inequality starting at 6, with a closed circle, going bigger. Notice in this graph, the overlap starts at the bottom graph, at 6. And then they continue to overlap, going off to the right. In interval notation, our low value is 6, with a square bracket, going up to infinity with a curved bracket. And that solves our compound inequality.